you know. All right, because a linear function, oops, I forgot the param. Like, no sooner do I start the video, I screw something up. If you have a linear function, whether it's a tangent or a secant, if I try to find the slope of the line tangent at a single point, I'm talking about something that would have the same slope. All right. If I'm talking about the slope of the line segment connecting the 2 points, either way I want to think about it, it's going to have the same slope as the line. All right. And if you think about the limiting idea, we would say that we start off with the secant, identify the slope of the secant, and then start slowly moving the coordinates towards each other. What would be happening? Well, I don't know where these points would eventually land, but I do know that wherever they land, they're going to have the same slope as that original secant, which was the same slope as the original line. So the linear function always has a slope, a tangent slope that's equivalent to the slope of the line itself. So that part answered itself. You don't need to justify it, or at least justify it on paper. We just have to find the other one. All right. Now, here's where we can start using our knowledge of functions to our advantage. So I'm going to take y equals 2 minus 2x plus x squared. And I'm going to look at that as the sum of 3 separate functions. So I'm going to look at this as 2 plus negative 2x plus x squared. All right, so I just rewrote the function, but I accentuated the different components. All right, so this polynomial function is the sum of 3 different monomials, but it's more importantly the sum of 3 separate functions. So I have a function here, y equals 2. You could actually even write them separately. Say y equals 2. Y equals negative 2x. And y equals x squared. All right, if I'm trying to find derivatives, I could use my knowledge of the slopes of different functions to help me kind of ease my pain a little bit. Y equals 2 is what kind of line? Horizontal. Horizontal lines have what kind of slope? 0. So my y, I'll write it as y prime. Anytime we use a prime, we're talking about a derivative. So if it's denoted as a y equals, we'd say y prime. You could also say dy over dx. We'll work more with that notation down the line. But anything that represents derivative. You want to go f prime of x, that's fine too. But we get a 0 for this. The second component is linear. So I know, just based on what I was talking about for the second piece of the function, that it has to have a slope of negative 2. The only part that I would need to figure out now is the x squared. All right, so then based on work that we've already done, we know that y prime here would be then 2x. All right. Now, if you had to show it with the limit definition, it's going to be a lot easier to work off of just the x squared than it would be to work off of the entire thing. Right? Because then you get the factor in by grouping, simplifying, and all that stuff. So all 3 of these components would then get added together to give you what it is that we are looking for. So, ooh, this is like a goldish color. I'm not really a fan. I don't know. Yeah, it's pretty much yellow. That's like the standard, I guess. Whatever, I'll survive. I'm just trying to highlight those plus signs. Because really what we're doing is we're taking the result of this, the result of that, the result of that, and adding them together. All right, so my y prime, in this case, would be equal to negative 2 plus 2x. All right, so whether or not that's relevant, I kind of glossed over that because I wanted to show you how to find the derivative in this particular context. but we do also need to verify that it's continuous function, right? So we'll address continuity. And that would be working off of f of x. So I would need f of 0, which in each case is 2. Whether I plug it into the first piece or the second piece, I'm going to get a 2 as a result. If I plug it into the appropriate piece, f of 0 exists, it gives me a result of 2. By plugging it into both pieces as the limiting component. So I would say limit as x approaches 0 from the left of f of x is equal to the limit as x approaches 0 from the right of f of x. And in both cases, I could plug it into either part and still getting a 2 as a result. All right, so continuity is a go. Because if it was not continuous at that particular point, x equals 0 is the relevant point here. But if, you know, there could be a bunch of different locations where it's not continuous. If it's not continuous at the relevant point, then you don't even look to find the derivative because you've already answered the question. If it's not continuous, it's not going to be differentiable. All right. So, but the reverse, the converse of that is not true. If it's not differentiable, it could still be continuous because it could be a corner or a cusp or something like that. All right. So we have continuity. Now what I want to do is address the differentiability at that point. And by the way, if it didn't give us the x equals 0, I would still be looking at x equals 0. And that's because I know this function is everywhere continuous, and so is this one. If it was not going to be continuous, it would have to be at whatever the break is in the graph. All right. In this case, there is no break. So what I'm going to now do is find the limit as x approaches 0 from the left of negative 2 plus 2x. And see if that's equal to the limit as x approaches 0 from the right of 2. All right, so what we're dealing with here are two limits that are not equal to one another. One is negative 2. One is a positive 2, just through direct substitution. Those are not equal to one another. All right, so it is not differentiable at x equals 0, so I don't have to worry about the tangent line. But just out of curiosity, what type of non-differentiability is it? Possibilities: corner, cusp, or infinite discontinuity. Corner. Corner is the only one where the slopes go to two different finite values. If either part of it's going to some kind of infinity, it's not a corner. Right? If they're going to the same kind of infinity, we're looking at a vertical tangent. If they're going to different infinity, so one's going down, one's going up, you're talking about a cusp. All right. Now, if the original function had an infinite discontinuity, well, that's a discontinuity, so it would not be differentiable at that location. So anywhere that there's like a vertical asymptote or anything like that, you'd be looking at something that's not differentiable. All right. Number 2, find the derivative with respect to x. Right. So that's just, you know, with respect to x. That's just saying that you have a function that's defined in terms of x. In terms of x is also said as with respect to x. Right. So so don't get thrown off by that. It means the same thing it's always meant. Is the function differentiable for all x? Well, first off, I already know it's not differentiable at x equals 0. All right, so let's start off with that. We have a vertical asymptote at x equals 0. Vertical asymptote is a discontinuity. Therefore, not, bless you, differentiable at x equals 0. All right, so we start with that. We already know, so we know part of the final answer, is it differentiable for all x? Well, no. But it did say specifically for us to find the derivative of the function 2 over x. All right, so we use the limit definition. F of x is 2 over x. I don't think this is going to be an issue, but I'll say it anyway just to kind of stave off any misconceptions. Because when I first started teaching calculus, geez, long time, so long ago, I don't even want to say. I don't think I emphasized enough that any type of function could work its way onto a test as the question that I ask you to find the derivative of using the limit definition. So on the test, I'm not going to ask you to do it like 5 times. I'm not even going to ask you to do it twice. I'll ask you to do it once, but any function that I give you is fair game. So it could be something polynomial. If you're lucky, you won't be. It could be a rational function like this. It could be a trig function when we get around to that. So anything's possible. So, and the reason I bring this up is because I had this mentality. Some people, students that I've had this mentality. It's generally not necessarily a good one. Where, well, I know the shortcut rule, so I'll just use that all the time. And then everything that comes out of my mouth is like blah 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 blah. And so when it comes time to do that problem on the test, those students have no idea what to do. And like I said, I don't think that's going to be a problem in here, but I just wanted to make sure I addressed it at the 12:15 mark on the video. That's the other thing. Now nobody can say, well, you never told us this could be on there. I have evidence. Of course, that being said, I'll probably screw up the upload and accidentally delete it and lose my evidence, but whatever. A little common denominator action here. Algebraically, you could feel free to skip a few steps because otherwise you'd be bogged down with the algebra and that's not fun. All right, so we have our common denominator of ax or xa, however you want to write it. This is really x minus a over 1, which you would then keep, change, flip. So it all consolidates into that. On the top, we have a GCF that we could pull out, so limit as x approaches a, I'll pull out a -2 times x minus a over xa times x minus a. So a little cancellation here. And so we end up with, when I replace the a with an x, -2 over x squared. Shockingly simple. Again, not the work, the final answer. Always the final answer. Almost always the final answer. So that's our derivative. And so now what I want to do is evaluate this. Because I have a location in this graph that I would be concerned about. So I might be looking at this function and say, okay, well, there's a break in the graph at 0, but that also corresponds to the vertical asymptote, which I know is a discontinuity, and I already know it's not differentiable at x equals 0. So the only value that I would be concerned about in this graph would be 0, and that's already been accounted for. Now, if this had something like -2 over x minus 1 squared, then I have to look at this function again, just to see if it's discontinuous or if there's any kind of vertical tangent thing going on. But the bottom line is, this function has the same issues as the original function, The only problem with it is that x can't be equal to 0 in my derivative function, but that's again been accounted for in the original function. Since I know a discontinuity means it can't be differentiable, I'm actually done with the problem. All right. Sometimes, and you saw this with some other problems, you have a function that's continuous everywhere, then the derivative has some not discontinuities, but at least a non-differentiability. But sometimes you have a bailout. I mean, and the only thing that made this problem tricky, not even tricky, just longer than it ought to be, is the fact that it said specifically to find the derivative with respect to x. If it didn't say to do that, then I would have stopped right here. All right. So, interesting stuff, I think. Now, if you happen to know, and just kind of a little sidebar here, we know that if we're given y equals 2 over x, we now know that its derivative, I'll write it as dy dx, is equal to negative 2 over x squared. All right. If we used a similar approach and just focused on the parent function, y equals 1 over x, we would get that derivative as negative 1 over x squared. The only difference being, and it's not really a difference mathematically, but the only dissimilarity is that this one had a constant multiple of 2, this one didn't, right? So that's actually a relationship that holds true. If you know the derivative of certain parent functions, then you can always figure out what the derivative would be of more complicated functions just by using multipliers or transformations. All right, so
I'm just a little bit confused on like what it actually means to differentiate.
Means to find the derivative.
Oh.
Yeah, the terms themselves, they're all basically, if there's any like tricky vocabulary word in this course, odds are it probably means derivative in some way, shape, or form. Right? Slope of the tangent line, derivative, differentiable, finding differentiability, anything along those lines. They all mean derivative.
Two questions. What would be the derivative of something like y equals 1 over 2x, or like y equals 1 over x plus 2 or something?
1 over 2x would be 1/2 times negative 1 over x squared.
Okay.
Yeah, because it's just a constant multiple of a half. And what was the other one you said?
If there's like it's like 1 over x minus 1.
Oh, 1 over x minus 1? That would be negative 1 over x minus 1 squared. But we'll have to get the chain rule before we can really dive into that one. Although we could do it with limit definition. I'm just thinking that people are limit definitioned out at this point. So, but I'll do it if you want. No, okay. So any kind of parent function, if you know its derivative, then you're in good shape. And so that kind of brought us back to the previous problem, where if I have y equals x squared, and I know that that has a derivative of 2x, then if I have y equals 10x squared, then I know what its derivative would be, because I know x squared has a derivative of 2x, I just have to multiply that by the coefficient of 10. Right? So a lot of different ways to get it. There are shortcut rules, again, that streamline this, but these are kind of like the beginnings of those shortcut rules, or at least the beginnings of understanding. So that, I mean, not to give too many speeches today, but I have found over the years that if you get to the shortcut rules too quickly, and I know people want to, because you want to stop having to do the work. I promise you, the shortcut rules for some of the more complicated situations don't end up being that short. So it's not like, you know, power rule is one thing, which we'll get to maybe today, we'll see. But when you get to product rule, quotient rule, chain rules, there's more rules beyond that. You got double chain rule, triple chain rule, you got multiple levels of the product rule combined with the chain rule. It's all a big mess anyway. And then we find something called a second derivative, which is finding the derivative and then finding the derivative of the derivative. So like you're never going to be off the hook with work, no matter what method we use. So there should never be a rush to try to get to what we call a shortcut approach. This stuff is to help you to understand why the shortcuts work the way they do. One, because I think you probably would be better off for it if you understand how things work rather than just, you know, like, here's a rule. But also, I mean, I don't want to invoke the College Board again, but they seem to be very concerned with that also. All right, so. And I think my method is good, because I mean, the emails from former students usually start coming in this time of year. So I got one yesterday. Students rocking Calc 2 right now in college, like destroying it, thanking me for it. Like, yeah, you're welcome, bud. You're welcome. I was so happy to. I'm always happy. I got my wall of fame over here. I don't know why I tucked it into the corner. It should be like in the middle of the room. But these are like some of the emails I've gotten. But, you know, like, you inspired me to be a teacher. All that stuff is great. But the ones where I am now doing well in college because of what I learned from you, or my favorite, my teacher sucks, so I've just been living off of your website, and that's what's gotten me through Calc 2, Calc 3, whatever. I'm like, yeah, that feeds the ego. That's good stuff. But yeah, he's going on to some serious calculus. Differential equations is a pretty tricky course. And I have no doubt that he'll be successful in that too. So there might be something to what I'm saying. That's all I'm getting at. That's all I'm getting at. But whatever. You're already here, so it's not like I need to advertise, you know. So what, if any, are the points of non-differentiability on the graph below? This one is pretty easy the way the question is structured, but it could be pretty not easy if it was structured even slightly differently. So we have points of non-differentiability, looks like, what, a -2? That would be a discontinuity. So we call that an infinite. They didn't ask us to state it, but I'm going to. Although I can't really write. X equals -1, what are we looking at there? Cusp. Doesn't have to be perfectly symmetrical to be a cusp. The two curves just have to bow in and merge from one into the other. All right, so they have to close in and then ease into the intersection rather than going directly. All right, even if one is a curve, they would still be a direct intersection if it's a corner. All right. Technically, I mean, this has always annoyed me. But they consider the people who write books on calculus for a living. This is where I completely disagree, but I got to go with what they say because otherwise you get stuff wrong on the exam. They consider a vertical tangent as a point of non-differentiability. Now, their line of thinking is that it's a point of non-differentiability because when you plug the number into the derivative, you get something that does not exist numerically. Like you get undefined. But I'm looking at this as, well, I found the derivative, I found it at 0. It gave me 1/0, which means that it's a vertical line. I look at the 1/0 in the case of slope, I look at that as being a valid number. So I don't see why it's a point of non-differentiability. I found the derivative right there. It's a vertical line. It's 1/0. But they disagree, and they seem to think that they're more qualified than I am. But that's only because they don't have jobs as math teachers, and so the only thing they can do to occupy their time and lives would be to write textbooks. So I'm going to go ahead and say that maybe they're not as great as they think they are, textbook authors, which is why we don't really use it that much. Anyway, at 2, x equals 2, that is also a point of non-differentiability, but because it's a point discontinuity. That one was kind of meant to be sort of a trick question. Ignore the little tiny gap between, I mean, on a test you'll have a clean graph that'll make sense, hopefully be visible, but that's not intentional. the open circle there, while you want to look at it and say, well, it's a corner because that's what a corner looks like, there actually is no point at that location. So the point of the point discontinuity trumps the idea of point of non-differentiability.
I think I'm not totally sure what a derivative actually is.
Slope
So.
at a particular point.
Okay.
So,
Well, why not say just slope then?
because people who had nothing better to do 200 years ago, and they had nothing better to do because they were born into wealth, decided on the vocabulary in their own native languages, then that got translated to English, and we're stuck with what they came up with. Yeah. Like, for example, in geometry, the reflexive property. The hell does that mean? I mean, I know what it tells us to do, but like, where do you come up with reflexive? Sine, the sine function. Well, that actually has a cool origin story, but like,
What's the origin story?
Well, the word sine itself is actually a derivative from the sinus term. So instead of actually being sine, S-I-N-E, like if you talk to anybody who's born abroad, they'll say sinus. And you'll think, well, okay, they're like really pronouncing that S again, S-I-N-E-S, sinus. No, S-I-N-U-S is what they're saying. And that's because it came from the idea that once the graph was generated, somebody was like, oh, that's kind of like sinuses. So let's just call it that. I mean, I know I make everybody sound like, oh, this is a dated reference, Spicoli, no? Fast Times at Ridgemont High. All right, watch that movie, that's your homework. So that's like the only 80s movie that I'll ever tell you to watch, except for Back to the Future and Star Wars movie and Indiana Jones.
Do we get extra credit to frequently watch it?
No, you'll just understand my references. So there won't be dead air after I lay one on you. So, but they're like, okay, so if I start here, I'm at, let's pretend this is the origin, and I go down, I go up, I go down, I go back up. Oh, it's like a sine wave. So let's just call it that.
How would you make that connection?
Again, people born into wealth with nothing better to do on their hands. So that's exactly what it is. I mean, literally nothing better to do. They're like, okay, so I don't have to worry about food, clothing. Well, my marriage has already been set up from birth, so I don't even have to worry about that. All right, let's see. I'm not really good at writing. Can't paint worth a damn. All right, let me just try solving equations or something. I don't know what else to do. So, I mean, if I took a math history course like 15 years ago. Oh, that's an exaggeration. I'm sorry. That's exaggerating on the favorable side. 25 years ago. And out of the whole course, I walked away with just that notion, what I just shared with you. The idea that people with nothing better to do came up with math. Right? Unless you're talking about calculus, in which case one person with nothing better to do came up with calculus, and somebody else who had more wealth than the first person stole all of his ideas and published before him so that he could get credit. Newton, Leibniz. So, as you go forward through calculus, you'll see that most of the notation, even though Isaac Newton is credited mostly with the development of calculus, most of the notation is Leibnizian, so Wilhelm Leibniz, von Leibniz, sorry. And so you start to kind of feel as you work your way through the courses who is truly responsible for all this stuff. Yeah, so it's pretty cool, I think, anyway. Oh, that's all on video. Hey. The only way this problem could be jazzed up more significantly, and just think free response on the AP, would be what, if any, are the points of non-differentiability of the graph below? Justify each using limits. So then you'd have to show the limit from the left, limit from the right is going to negative infinity, right? For the original function, illustrating the infinite discontinuity. At the cusp, what we'd have to say is that the limit of the derivative, so you can use the ruler test if you want, but the limit of the derivative seems to be approaching positive infinity in this direction, and then negative infinity in this direction, so they're going to two different infinities, so that justifies the cusp. Same infinity, so again, the ruler test, you're following the curve, it seems to be going to negative infinity. You're following the curve, it seems to be going to negative infinity. All right, so same kind of infinity gives us a vertical tangent. The point discontinuity just shows that that's the trickiest one, because that has the extra step. You have to show the limits from the left and the right are going to the same place, but the function does not exist at that point. So I'd have to also state that f of 2 is not something that exists. Right, so it's just a lot of extra steps, none of which is overly challenging, just it's an annoying extra level of work that you have to do. Questions on the textbook? Oh, sorry.
I don't understand the ruler trick.
Oh, the ruler trick? Oh, that's like my favorite in this.
How would we write that on a?
You just put the results.
You could say.
You say, no, you just say limit from the left
Okay.
going to 0 is infinite or whatever it is. So you're not looking at, because people have, I think anyway, in the past, gotten confused with things like arrows on a graph. You know, like when they talk about increasing and decreasing, they say it's decreasing because the arrow is pointing down. It has nothing to do with that, it has to do with the slope. So the ruler gives you a sense of the slope. So what we do is we start off with a point that's somewhat far. I'm going to look at 0 here. Start off at a point that's somewhat far away from that location and estimate what the tangent line slope would be. So actually the ruler becomes the tangent line.
Oh.
Here you can see it's a negative slope. And now as we work our way closer and closer, we start getting closer and closer to the true slope at that location. And since it seems like it's going vertical, we can assume that, well, it's going to be a vertical tangent, that's number one, but also the pitch of the ruler is in the negative direction. So right before it goes vertical, it's as negative as it can be. So then coming the other way, follow the slopes, you can see that the pitch of the ruler is in the downward direction. So again, right before you get to that location, it's as negative as it could be right before it goes vertical. In both cases, we're going to negative infinity. All right, so off the graph, it's pretty easy to see if you have a sense of this idea. Breaking out a big old ruler in the middle of a test just for one problem like that, I don't know how practical that is, but you know, pencil, pinky, use appropriate apparatus. Anyway, okay, so there's like only 5 minutes left, but whatever. Were there any questions on the textbook assignment? Did we do the textbook assignment? 17? Ooh, that's a good one. All right, so find all values of x for which the function is differentiable. All right, so these problems on this page are telling us to find the locations where it is non-differentiable, but basically differentiability is everywhere else. So if I find locations where it's non-differentiable, then I'll be in pretty good shape. Oh, it looks like a difference of cubes up top. May or may not be relevant. So you still need to know how to do it, although in not all cases will it matter. All right. I do need to factor the bottom here because I know if a function is not continuous, it's not going to be differentiable. So let's address that component. All right, so we have vertical asymptotes. And, you know, I'll list the factors of the top just so you have it. X minus 2, x squared plus 2x plus 4. And that, the only reason I'm doing that is just to demonstrate that there is not a hole in this graph. So there's no point discontinuity. The only time a point discontinuity would happen in a graph, unless it's piecewise, would be if you had a common factor top and bottom in a rational function. Not the case here. So the only discontinuities would be the vertical asymptotes at, that's a v for some reason, x equals 5, x equals -1. All right, so now it's a matter of addressing the derivative. So what we want to do is make a determination of what that derivative is going to look like. But that's a pretty beastly looking problem. The kind of problem that a shortcut rule would be very helpful for. But at this point, the calculator is where we're going to go. Just understand one thing that I neglected to mention. I apologize for this. So if I kept you up last night, I really, really feel bad. But the textbook doesn't always distinguish between what it considers to be calculator problems and what would be analytic problems like the AP, which is one of the reasons why I don't like it, because it should say, do these by hand, do these specifically on the calculator. But it'll say in some cases do it by hand, but then it never really tells you when the calculator is the best way to go. I mean, maybe a couple of times, but not often enough. So this would be one of those situations, at least at this point in the course. So take a look at the graph. I have the discontinuity at -1, and I also have one at 5, but I don't see a remainder of the graph. So that means my window probably needs a little work. Looks like it's getting pretty big. So let me go up to like 50. See what the story is there. All right, so we have some more graph. I'm looking at something that does not appear to have any kind of corners, cusps, or anything like that. But what I can do is turn this graph off and turn my derivative graph on. And take a look at that. If I see any other movement towards infinities at this graph other than 5 or -1, then I'd be looking for vertical tangents or anything along those lines, you know, like cusp and things like that. Corners typically only happen when you're dealing with piecewise functions or absolute functions. So at this point, our discontinuities are infinite only at these particular locations. All right, so we'll pick up with this tomorrow and go from there.